damages would be interested. We go another step further by taking those detailed flood maps and mapping it on to census and real estate data. And my young colleague Kevin Smiley did that, and that's why that number I wanted to show you on before on the cost I don't like anymore, because there we assume that the properties are equally distributed throughout the flooded area. Well, of course they're not. People live in specific places. As you can see here, with the shaded hexagons are those homes that under this particular scenario were flooded because of climate change, and it's not uniformly spread out. When we go to our 19% precipitation increase in the 14% flooded area, we find that climate change flooded with an additional 32%. So 33% of the homes in this county that were flooded would not have been flooded without climate change. We also found that 75% of the flooded homes were, in the other case, were outside of the 100-year floodplain and left uninsured, which sort of explains, I think, some of the disparity in the NOAA's total loss of $155 billion versus the reinsured estimate. And so, making a leap of faith that all these properties are more or less the same value, we'll say that I will say anyway, that global warming caused a third of this damage, or that climate change cost $50 billion, which seems like a lot of money. Going into the census data, we looked at it as a bunch of different ways: single versus multi-family residence. We didn't see much effect there, and mobile homes, which was not going to be. We did see some interesting results with income and race. In particular, what we found is what I'm calling an environmental injustice. And about a third of the homes in this county are low-income Hispanic households, but half of the flooded homes. Now, it turns out in this case, half of the flooded homes that were flooded without climate change were low-income Hispanic, as well as those that were just about half that were flooded because of climate change. That may be because we looked at this only at very shallow flooded fields. We now move, let me summarize Harvey though. So regardless of the precipitation change estimate, whether you use 19% or 7% or 40%, there's this environmental injustice. It's an existing injustice. We think it's probably just exacerbated by climate change. We didn't show it in this study. We also found that in the high income, mostly white neighborhoods, the richer you were, the greater the financial damage. It makes sense. You have to go behind to move around. But also in low income Hispanic neighborhoods, the poorer you were, the greater your relative financial damage. And we don't know exactly why, but my speculation is that both groups live near the water. The rich people have a very nice view, and poor people are looking at it and finding it. I think that's reasonable. Oddly enough, we didn't find any statistical incomes in other groups, particularly in the African American community. And our speculation there is that the African American community has been in the Houston area for a longer period of time than the Hispanic community. And so the good places were already taken, so that they were forced to live in more flood-prone regions. So I'm calling this end-to-end attribution. To summarize, a degree of global warming caused 20% more rain, about 14% more flooding, about 32% more flooded homes, and about 50 billion. This data is available if anybody's interested. I want to dive into the environmental injustice a little bit more. For another storm this is in revision right now, we looked at Hurricane Ida's remnants. Ida was an interesting storm. It made landfall around Louisiana and then exited New York and New Jersey. And flooded that area with devastating results in Queens. People drowned in a so-called garden apartment that was living in the basement or in the cellar. So we thought about two plausible attribution statements: a really conservative one and then one that was reasonable. Clauses platform and twice clauses. Our best estimate on the twice clauses platform increase in precipitation is that about 500,000 more people flooded because of climate change. There's something in the U.S. Called the Social Vulnerability Index of the Climate, the Center for Disease Control tabulars, and it's a measure of how vulnerable you are as an individual compared to both the country as a whole, as well as where you live. And you can see that the darker blue colors are the more vulnerable parts of the United States. The upper Midwest and the East Coast are less vulnerable for a lot of reasons. So we're going to use this index and map it on to these flood data. Oh, I should have mentioned the one on the left is the change in the depth due to climate change. The one on the right is the change in what they call head, which is the rate at which, in this case, the maximum rate at which the waters rise. And you can see they're in different places. And in fact, in the head, the maximums appear to be in close to New York and close to Queens, where people go. And so we use that social vulnerability index to define an inequality index using something that looks like a Gini score. If you're familiar with this kind of thing. And basically, you map the percentage as a function of your vulnerability, what fraction of people are in. And if we were doing the entire United States, since it's normalized for that, it would be along the problem. But in New Jersey and New York and Pennsylvania, it's pretty well off. So it actually, this is above that. And then the flooded population, because poor people were more impacted than rich people, is below. And so the difference in those areas is our index. And what it says is that we found that there was a rather moderate inequality at a third of a meter that increased as we got to 50 per meter. But more interestingly, we thought this as a function of different global warming levels, and we did 4 of them here. We did the world there was, 2 past amounts, and 2 future amounts. And we see at these deeper levels, there's a very strong influence of climate change on this inequality. And so, and this is even worse at 2 meters and 3 meters. And so climate change did exacerbate the environmental injustice. So it's a future work. Well, I think there's a lot of future work, and I don't have time to go through all of them. The one I think is most interesting that we're sort of working on now with Nathan Deb and Rob Hedlund is try to do a storyline on saltwater flooding, on storm surge. And Nathan has some simulations of Hurricane Ida's storm surge, where there was a 5-meter storm surge in Fort Myers, Florida, which pretty much wiped the home right off the foundations. And so it's an interesting storm because you have this big, devastating storm surge on the coast, which caused a lot of damages. But then a few days later, all the rainwater ran through the system. Florida's rather porous. It took a few days, but a few days later, there was a wide area flooded with fresh water. And so the question I've been trying to get a handle on, but no one knows. I think insurance companies know, but nobody I know knows the answer to this. Which caused more financial damages, the storm surge or the freshwater flooding? I do know that more people died in the freshwater flooding. Maybe a bit of a surprise, since that actually took a while. It's like of order in quarters. So I have some questions about attribution for Tropicana to consider. Well, I showed you that supercloudless cloud run seems to be happening a lot with these big storms, which is really bad. And certainly increases freshwater flooding. And I think in many cases, maybe always, the poor take the brunt of the impact. I mean, that's true for not just for climate change and storms, for lots of things. It will always be the worst of it. I think we need better detection variables for wind speed. The Saffir-Simpson scale doesn't work. It's 0.1. I think it's too noisy. We see it in future storylines, but not in the past, so it hasn't really emerged. We've a couple of studies, including one that Tim Toss and I did with category 60, showed that trends in potential intensity are attributable, but we don't have that for action. I think that attribution of storm surge changes may be tractable. It's going to be tough though, because this storm surge is so dependent on the trajectory of the storm. And so we have, that's going to be a tough. And I raised TC frequency. It's a controversial study. There's an interesting set of exchanges between Saffin Chan and Perry Emanuel I'm on the chain, which says the number is going to go down using, or did go down actually, using a 20th century analysis versus Perry, who argues that wins. That would be, if you're interested in this subject, reply and comment and reply. I didn't get a chance to really talk about loss and damages, but I'm going to put those slides in with the deck today. TC mortality in developing nations is very, very large. The United Nations Framework Convention on Climate Change, through the Conference of Parties, the 27th and 28th, Cairo and Abu Dhabi, established loss and damage fund to help those nations that are, quote, particularly vulnerable to the impact. And that fund has been sort of set up, or some money in it, but not really enough. And it's an inherently political process. I don't think we should be naive about that. But I would like to see attribution science be able to at least provide the best information, and then the politicians make decisions that they make. At least they will make informed, there will be informed decisions, whether they're right or not up to me. We're going to discuss high risk net 2. We're going to discuss high risk net 2 tomorrow, I guess. And so I'd like people to think about what experiments are most useful to this graph. Which one, I have ideas about what are useful to me, but I think there are other interests that are why. And I think that's it. Thank you. Time for questions?
Yeah, how should I? Yeah, there was 4 people, so. And just keep in mind that we can discuss about all this later, so don't stay stuck with your questions.
Okay, I have a lot of disconnected questions, so maybe you can answer whichever one you think is most interesting. Okay, or maybe I'll let you choose. I'm interested. I don't do a lot of attribution studies, but I'm always like, how do you know that the covariates intervene in a linear way? So I see when you condition your GEV, you always have linear relationship with the covariates, and I'm always wondering, isn't that making implicit assumptions that then matter for attribution? That's
let me take that one. I got an answer to that one. The answer is yes. That's what we're asserting. We can test that by putting confidence intervals on the values of these coefficients. And basically, if at a given statistical level of confidence, if that confidence interval encompasses 0, we say, no, that covariate isn't important.
No, but if I throw
that's true sometimes.
Yeah, I guess my question was more like, how do you know whether to throw in CO2 or log of CO2?
Oh, it probably doesn't matter.
Okay.
Yeah, we use log because that's what they use.
Maybe the other one I'm curious about is, have you looked at different types of SVIs? Like, how the social vulnerability index can be decomposed into different categories.
No.
And
this is the first one we've attempted. And in fact, this is mostly work from my co-author, so I don't actually know much about that. If you know something else about other vulnerability indices,
I hope people,
particularly ones in other countries, particularly ones that might relate rich countries or poor countries, I'd be very interested.
Yeah, nice talk. So I'm wondering, so you showed looking at counterfactual world precipitation for various storms and how it's increasing today relative to the counterfactual world. And you also touched briefly on in your summary about TC frequency and how I think there's no real consensus today about how we expect frequency to change globally, at least in the future. So I guess my question is, do we know that that the net risk of this heavy rainfall from TCs in the future will actually increase, given that it's possible that if frequency of TCs decreases, perhaps despite like any given TC having heavier rainfall, the return period could end up decreasing or increasing.
Yeah.
So I'm curious your thoughts on that.
I
And
know
how
what you're asking, and it relates to what Jim Cosson and Masaki Sato and I wrote on this subject for chapter 11 of IPCC AR6. There we wrote a very conservative statement. We wrote the fraction of intense tropical cyclones will increase. There was a lot of pushback from the countries, particularly those vulnerable in the Caribbean, to say something about the number. And we didn't feel, although all three of us felt that we were on the decreasing, climate change was decreasing the number of figures. We didn't feel like there was a consensus on that. And so I dreamed up a scenario where you could have the risk of the number of intense hurricanes with heavy rainfall increasing for a while. But if the decrease in total were large later on, that it could go down. So you could have the risk going up and going down. So I don't think we really know. And so that's, I'm kind of hoping that we can address these questions, through the seeds discussion and the expertise in this room.
Thanks.
Thank you very much. For the interest of time, we will move on to the next speaker. But so next we have Claudia Pascaro from the University of Milano. And I guess we will move to a more dynamical topic, right?
Yeah, we go from the effects of tropical cyclones on population and our communities on more of a focus on interactions, because this morning we have been told that we have the key of Tropicana is interactions. And so it's the interactions between the troposphere and the stratosphere in tropical cyclone evolution. And by the way, this work has been done over the last year or so, jointly at the University of Milano di Coca, where I work, and Eastavian in the group of Caroline Muller. So I want to start with something that is, I'm sure, very familiar to everyone, the potential intensity of tropical cyclones. That refers to a mature storm. Mature storm means that it's a steady state, it's a statistically steady state where the energy input at the Orsay interface is balanced by the energy dissipation in the frictional layer. And the theory that Emmanuel over the years developed actually assumes that, considering that convective time scale is very short, we can assume that the troposphere is neutral to moist convection. So starting from those assumptions, then Emmanuel derived this potential intensity that is related to the thermodynamical disequilibrium at the Orsay interface, and to exchange coefficients. And there is also this efficiency that is the ratio between the sea surface temperature and the outflow temperature divided by the outflow temperature. The outflow temperature is essentially the temperature at which the outflow happens, meaning that, and this is the temperature at the equilibrium level. So if you start from an air parcel near the surface, you ask at what level does this air parcel become neutrally buoyant? And at that point, that's essentially the outflow. Typically, this is the tropopause temperature, but as I will show you next, there can be quite a bit of variability in the outflow temperature. So as I said, this is a sort of a theory for the steady state. And it was tested very successfully in many different models. I took those figures from a paper of Akin in 2011, where he essentially took the Rotuno and Emmanuel. Actually, in this version, it was the Brian Rotuno model of, it's an axisymmetric model of a tropical cyclone that spins up, and if you start from a finite amplitude perturbation, it develops a tropical cyclone whose intensity is really closer to the potential intensity, as you can see. Do I have a pointer? No, but I can show. No, I don't. Okay. Do I have a pointer? Oh, yeah, here. Thank you. Okay. The mouse doesn't. No, I don't. Anyway, it doesn't matter. No, don't worry, don't worry. What I want to say is that initially and for some time, the tropical cyclone stays in this potential intensity limit, but then there is a decay. And of course, we're not interested in the decay if we are really thinking about the evolution of a real tropical cyclone, because the conditions vary. So this is an idealized setup where the environmental conditions are homogeneous, they are not changing. And of course, there might be many different reasons for having a tropical cyclone decay. But I think it's still important in order to understand the dynamics of those tropical cyclones. So actually, Hakim noticed that if you wait long enough, then the tropical cyclone is really not in equilibrium and eventually decays. This decay is related to the fact that in these models, remember, I said at the beginning that the models assume essentially a troposphere which is neutral to moist convection. And so the way radiation is incorporated here is simply by relaxing the vertical profile of temperature to a moist adiabat. And the question becomes, what moist adiabat? The moist adiabat that is valid for the environment away from the tropical cyclone might be not the right one for the region in the tropical cyclone I. And that's because the increased air sea fluxes generate an increase of temperature and moisture in the boundary layer, and therefore the moist adiabat that is representative for that surface air conditions is actually at a higher entropy than the moist adiabat that would be valid for the rest of the environment. So essentially what is happening is that in these models, the temperature profile is forced to relax to a low entropy moist adiabat. And therefore, and this forces a cooling and a drying environment. So, and we all know that a drying environment is not what tropical cyclones like. And of course, the tropical cyclone will die off. And then what Hakim did was also modifying the radiation scheme. And rather than having a relaxation to a moist adiabat, and considering that you wouldn't know which one would be the right moist adiabat, he used interactive radiation, and he showed that indeed the tropical cyclone reaches PI, the potential intensity, and it stays over there in a statistical sense. And he also showed that indeed the moist adiabat for the I wall, which is the red one, is on a higher entropy than the moist adiabat that you had in the beginning. So everything makes sense here. But then over the last years, people started looking at these tropical cyclones, not in axisymmetric models, but in fully 3D models. And actually, the origin of those studies came from the fact that self-aggregation of convection was discovered, first in non-rotating environment and then in a rotating environment. And I think those two papers were already cited this morning in the previous talk. The focus of those papers was really to look at the feedbacks, the radiative feedbacks and the surface flux feedbacks in the aggregation of convection during the intensification phase. So the focus was not on what was happening afterwards, but it was only in the intensification phase. But both of those work show that there is a generation, an intensification of the tropical cyclone, which then doesn't really reach a statistical equilibrium, but eventually it dies off, or it starts oscillating, as in the Muller and Rom's paper. Both of those models use the same kind of model, but the similar results has also been presented without, again, focusing on the decay, but just on the span-up phase, using a different model. So this kind of behavior seems to be relevant across case. And so we thought it was interesting to understand why the system doesn't really reach a steady state and what is causing the decay of the tropical cycle, at least in the models. So we use the same configuration as in Muller and Romps. So this is well, this model is SAM with anelastic equations resolved on a grid. Actually, let me start it. On a no, okay, yeah. We have a 4 kilometers spatial horizontal resolution, and again, as it was already said before, the cyclone intensifies. It reaches like a Category 4 hurricane. And then it de-intensify going to almost a tropical depression, and then the cycle repeats itself. During these oscillations, Cape is also oscillating a lot. So convective available potential energy is relatively large in the beginning phase when there is no deep convection. When there is deep convection, during the intensification phase, Cape is removed. So we go towards a moist adiabat. And then rebuilds again, and then decreases again when the next round of deep convection occurs. So the fact that there is a Cape rebuild, I mean consumption and rebuild, it really means that the troposphere is not really a moist adiabat, and so that's also why potential intensity is not reached, because it really requires the moist adiabat. So what's causing these oscillations? In order to verify whether, I mean, in order to understand where why the troposphere is not on a moist adiabat, we decided to look at moist static energy, which is the quantity that is really conserved during a moist adiabatic process. And if we look at the moist static energy of the boundary layer, which is shown here in blue, we see that near surface air initially has a relatively low moist static energy. Then wind-induced surface heat exchange increased the moist static energy in the surface layer. And so there is a rapid increase of moist static energy. And then what I want you to notice is the fact that the moist static energy in the near surface layer keeps increasing while the cyclone is already decreasing. So we kind of think that considering that moist static energy, I mean, yeah, the moist static energy of the surface air is increasing, that would mean that the tropical cyclone can be fueled even more and can intensify even more. But instead, that's not true. That's not the case. So it means that the weakening of the tropical cyclone is not really due to the fact that the moist static energy at the surface has reached a plateau. Of course, it keeps increasing. And then if we look at a Wehner type of diagram, where we have time and altitude, and this is the moist static energy in the beginning. The fact that there is a homogeneous moist static energy means that we are close to the moist adiabat, of course, in the troposphere. And then there is a stratospheric level of moist static energy, which is larger, but the whole troposphere is kind of homogeneous in that. Then the cyclone picks up, and the moist static energy, because of the enhanced air-sea heat fluxes, increase. And the tropospheric moist static energy increases as well. But we see that in the upper layer, actually the moist static energy becomes even larger than in the lower layer. So considering that this is air that's actually going upward, almost adiabatically, then how can we have a value of moist static energy higher in the upper levels than at the lower levels? Where is this energy coming from? So clearly this demonstrates the fact that the process is not adiabatic. There must be a diabatic source of heat in the upper troposphere. And clearly the possible origin of these are essentially two. One is a stratospheric exchange, sorry. Remember that the moist static energy in the stratosphere is very large. So if we're able to bring down a little bit of that moist static energy, clearly we can increase the moist static energy in the upper layer. So the first thing that we looked at was the exchanges with the stratosphere that are here quantified, looking at the vertical velocities at the tropopoles. The median is shown in green, and the purple and red show the interquartile range. And so we see that when the deep convection picks up, then we have a lot of updrafts and downdrafts at the tropopoles, and clearly those are suggestive of exchanges, of air mass exchanges between the troposphere and the upper troposphere and the lower stratosphere. So yes, it is possible that this diabatic source is actually mixing with stratospheric air. So there are stratospheric intrusions that are causing a warming of the upper troposphere. And we see why this is important. Then another possibility for diabatic forcing is actually radiation. And so we tested this hypothesis by running another simulation where radiation was fixed, so it was not interactive, and the process was still there. So that's not the key. The radiative warming is not the key, but the stratospheric exchanges are indeed the key for this upper level warming. And let me go back here, to say that when there is this upper level warming, the equilibrium level drops significantly. The equilibrium level is shown in black. So it means that near surface air is not buoyant above that line. And so it means this is a fundamental constraint on the uprising motion. The uprising plumes are actually slowed down above this equilibrium line. So rather than reaching the tropopoles, the plumes are forced to stay below, or are limited in their ascent to stay below this line. And when this happens, clearly the outflow temperature is increased a lot. And by a lot, I mean that we noticed a change in the outflow temperature from about 200 Kelvin to 250 to 60 Kelvin. And this means this large increase in outflow temperature means that loss of latent heat that is released at 200 Kelvin, because essentially there is no water vapor at 200 Kelvin. All of it goes into liquid water. But actually at 250, 260, there is a significant amount of water vapor that stays in there. And so not all the latent heat can be released. I will skip on the dependencies on the domain and such. And I would go into the analysis of the NICOM diamond simulation. So we took, here it's running. We took a diamond simulation of summer. It's run at 3.5 kilometers resolution. This is not idealized, but it's in the real, not in the real world. It's in the real diamond world, of course, but it's in a GCM at high resolution. That has several cyclones, and here I'm showing you one of them. Its evolution is shown in here in terms of surface wind speed. And here we see the same type of analysis done on more static energy. So actually the intensity picks up and then decreases. We can't follow it to longer times simply because it makes landfall. So we can't really follow his full decay. But we can see that the moist static energy has a similar behavior to the one that we observed in the idealized settings, meaning that the peak in the boundary layer moist static energy is actually after the peak intensity. So that's limiting the moist static energy in the lower level is not the reason for limiting the intensity. And actually the moist static energy in the upper level shows an increase at the time when peak intensity is reached. So again, it seems that even in these cases, the interaction with the stratosphere might be the key for limiting the uprising motion of the columns, and therefore limiting the amount of latent heat that can be released. Well, in observations, we don't really know whether that's important or not. What we found is a paper that describes the temperature change at the tropopoles, and it shows that in a Bolaven typhoon in almost 10 years ago, or a bit more than that, that shows a cooling above and the warming below. So a dipole, and this would be consistent with the stratospheric tropospheric interaction. So with bringing up some tropospheric air and bringing down some stratospheric air. So that's a signal that we would expect. But from here to say, I mean, from these data to say that indeed that's what is happening, I wouldn't be so sure. I mean, we need more work clearly in this thing, but at least it's consistent with that. So let me first go. No, okay. How do we put this in context of potential intensity or revisiting a potential intensity theory? Well, I wanted to start from the fact that 10 years ago, Lin et al. In 2013 modified the potential intensity in order to account for the sea surface temperature reduction associated with the wind-induced mixing in the upper ocean, thinking that, of course, we know that the winds stir the ocean and they're bringing up cold water, and that means that the cyclone, when it passes over the ocean, feels a temperature that's not the pre-storm temperature, but it's a lower temperature. And so the potential intensity can be modified in order to account for this reduced sea surface temperature generated by the action of the wind itself. And so rather than using sea surface temperature in the efficiency term over there, they propose to use a pre-cyclone depth average temperature. So temperature averaged over the first 80 meters of the ocean was a better, they claimed that there was a better measure, better estimate of the actual sea surface temperature felt by the tropical cyclone when it goes over a portion of the ocean. And indeed, these improved the relationship, made the PI and the potential intensity and the actual intensity reached by cyclones closer to each other. So the question becomes, in this case, it was a correction for the mixing induced by the tropical cyclones at the bottom that would correct the potential intensity. So the question now comes, should a similar correction be applied to the upper tropospheric boundary, not only to the bottom tropospheric boundary, because at the upper tropospheric boundary, there is interaction. For strong cyclones, there is interaction with the stratosphere, and this can modify the outflow temperature, as we showed. So right now we are working towards a modification of the potential intensity to account for that. So fixing not only the bottom boundary, but also the top boundary. And let me conclude by saying that, well, the assumption of adiabatic ascent of boundary layer air for strong cyclones may be unrealistic. Strong cyclones are necessary because otherwise those plumes do not really go through the tropopause. And numerical models show that exchanges between the upper troposphere and the lower troposphere stabilize the upper troposphere, which cannot be considered neutral to moist convection, but instead it becomes stable. And so the ascending plumes are prevented from reaching the high levels, and the outflow elevation is effectively limited to mid-troposphere rather than going all the way up to the tropopause, rising the outflow temperature by several tenths of degrees, and thus limiting the release of latent heat by condensation. So I would also like to mention the fact that I haven't talked at all about the fact that stratospheric descending air has also been associated with rapid intensification, but that's not something that I discussed today. But if some of you is interested in that, I would be happy to talk about it. Thank you.
Thank you very much. Time for a few questions.
Thank you. I didn't quite understand what triggers the stratospheric the stratospheric air to go down, and what triggers that mixing? What is the origin of that mixing?
Okay, so it's actually the ascending plumes that are going. Yeah, we have ascending plumes going up, and that generates turbulence and mixing, meaning that also stratospheric air goes down because of the mixing induced by that. That's at least what we think is happening.
Okay.
There is also the possibility of having a secondary circulation developing there, meaning that there is subsiding air, actually, that's driven by radiative feedbacks, in the sense that Where you have clouds and where you have no clouds, you generate a secondary circulation that generates subsiding air. So probably it's a mixture of those two things that is responsible for these intrusions of stratospheric air into the upper troposphere.
Liz, maybe if you want, you can start switching the presentation.
Yeah, I realize you skipped the slide, but what was the effect of the domain size on this?
Thank you for asking. I have a slide ready for that. No, because this is idealized setting in doubly periodic domain. And so we were wondering whether the actual settings was playing an important role in this process. And so we modified the domain size by increasing it by a factor of 4, I think. And eventually we noticed that in that model, there were 3 cyclones developing at the same time. I mean, not exactly the same time, but differently. So meaning that it was large enough to let different cyclones develop. And this mechanism was still there. So we had, and we analyzed the boundary layer moist static energy, the upper tropospheric moist static energy, and everything was still qualitatively the same. So it wasn't changed. So that's not the key. It might be that actually the timing of the oscillation is related to that. The full oscillation, which I haven't talked about, is modified by, is sensitive to the domain size, but the actual drop of intensity is not.
Thank you very much. We will now move on to Liz Ritchie from Monash University, talking about, I believe, tropical cyclones in the Australian region.
So I'm going to do something a little bit different in this talk. I'm going to more just give you a bit of an overview of a few different pieces of research that we've been doing and we are doing that I thought was kind of relevant to these next couple of weeks. I thought that might help, you know, maybe possibly trigger some interest in some conversations later on. So you shouldn't have to use your brains too hard during this talk, except that I'm going to switch topics around a little bit. And the other thing I did want to say was that unfortunately I didn't go back and change my numbering system here. So we'll focus more on what just each of the little bits are. So I'm going to talk a little bit about some research we've been looking at with globally historical impacts and future changes. When I say globally, we've been looking at some different basins and some of the work attributed to originally PhD students working with me, Denise, Kim Wood, Lynn Tran, and Rabia Kabir. And then I'm going to switch topics and talk about this other thing we're working on, which is looking at impact of tropical cyclones on the Earth energy balance. And that's mostly from a historical perspective at the moment, but it has implications for you know, changes in a warming world. So I wanted to talk about that a little bit as well. I won't get to the oceans bit because we're just a little bit too much in here. So the first topic, just thinking historically about tropical cyclones and how they've changed over time. So some of the work we've been looking at has been just working with best track data sets and looking at things like track density. This is not work that is necessarily different to what other people have been doing, but we've been looking at, you know, track density. So this is a the little thing sitting on here that's blocking my view of my, there we go, that's better. So this is 80 years of best track global tropical cyclones using specifically the WMO regional center best tracks for each of the regions. So this is just focusing on those particular best tracks, but I am using the IB tracks data sets to generate these. And what we want to do is understand how tropical cyclones have impacted regions historically, how they've changed over the past 40 to 50 years, depending on how good the data are going back that far. Different regions have better data, and some regions have data that's really only reliable going back about 40 years, and then how they might change in the future. Some examples are up here. For example, this frequency of location at landfall, not something particularly unusual, but we can also look at frequency of, there's my arrow, of particular wind thresholds. upon landfall. So in this case, I'm showing just an example in Southeast Asia of the frequency of winds at least 34 knots when they make landfall. In the bottom is the accumulated rainfall that we get from TRMM data sets. So we want to look at exposure impacts, potentially risk. We also want to look at changes to tropical cyclone structure. So these are the sorts of things we've been looking at. And at the moment, our focus regions have been mostly because of where my PhD students have been from. They're, of course, very interested in their own regions. So we've looked at Southeast Asia in particular, Bangladesh, and out of the North Indian Ocean. And then I've just started to look at the Southern Hemisphere, but I won't show any of those results. And I just want to give you a little bit of a flavor of some of the things that we can get out of these data sets. So here we're looking at position frequency. So you can see this is Southeast Asia. Put my glasses on so I can see what I'm doing. So here, 50-year position frequency in Southeast Asia upon landfall. So again, focus on landfall. Over here, the duration. So in hours, the duration of tropical cyclones as they pass over particular regions, which is of importance because the longer you feel particular levels of winds, the more damage you may get. And then over here, I'm showing you 25-year position difference. So this is showing same sorts of results that other papers have already published, where you can see that the frequency of landfall is shifting in Southeast Asia and in the Western North Pacific, where you're getting a decrease over places like Vietnam, and an increase further up in sort of northern China. And then again, re-showing that frequency of winds with a threshold of at least 34 knots. Okay, so we can get a look at these kinds of impacts. We switch over to the North Indian Ocean. We're showing a similar sort of thing, but just to show you can do it in another region. So here's North Indian Ocean. Particular impact you're going to see later on that was really focusing on was Bangladesh. But here you can see the track density. This is over a 40-year period now. And then we can look at the changes over time. And these are 15-year differences instead of 25-year differences because we don't have quite such a long data set to look at. But we can split it out into the pre-monsoon, the monsoon period, and the post-monsoon period. So we can do these kinds of either seasonal differences and impacts, or we can look at this in relationship to different climate indices. So I did a lot of work looking at ENSO and PDO, particularly in the Southeast Asia region. You can also look at this frequency of particular thresholds of winds. So here I'm showing again North Indian Ocean, but you can look at a landfalling, the frequency of at least 34 knot winds or the frequency of at least 50 knot winds. And then you can look at how that's changed over time. So in this case, a particular interest, we're seeing an increase in frequency of at least 34 knot winds in the Bay of Bengal, along the Indian East Coast and up into Bangladesh here. You can also look at rainfall. And so this is from the TRMM data set. You can look at the total accumulated rain, for example, in various regions in terms of millimeters. And then you could look at this in terms of, again, 25-year, well, not 25, 10-year differences with the TRMM data set or 15-year differences, hopefully soon. But here we're looking at how it changes seasonally. So this is another way. So you can see there's a seasonal impact of tropical cyclone landfall in Southeast Asia. And so they start off much closer to the equator initially, and then they start to move further and further north during the peak of the season. So you see much more of the impacts during the peak of the season, of course, and then they start to retreat back down towards the equator again by the end of the year. And again, you can do the same thing in the North Indian Ocean, where you have the total tropical cyclone rainfall over the 20-year period of the TRMM data set, and then you can split it out into the pre-monsoon, the monsoon, and the post-monsoon rainfall. And you can split it out by IOD, and you can split it out by ENSO and look at how the impacts change based on those climate indices. So we also look at future changes. So historically, we use the best track data sets, but to look at potential future changes, we do simulations, obviously. So we use the WRF model to simulate tropical cyclones over a historical period. In our case, we've been focusing on landfalling tropical cyclones. So we've been choosing the landfalling tropical cyclone subcategory of all tropical cyclones in Southeast Asia and in the North Indian, well, at least in the Bay of Bengal. add a pseudo-warming perturbations to it from CMIP6 models, ensemble of 28 models for Southeast Asia, and then we actually use just the access model for North Indian Ocean. And then you rerun the WRF simulations with perturbations added for different SSP scenarios and also for different periods. So we looked at the 2030s, the 2070s, and the 2090s. And most of what I show you here, just as examples, will be from the SSP 370 from the 2090s, so the end of the century. But again, you can, with these simulations, in this, for Southeast Asia, she ended up with 117 different tropical cyclones. And then she did 6 different climate perturbations on those. She ended up with a very large database to analyze, which was quite nice, really. So here on the left-hand side, we have the medium scenario, the 245 scenario for the 2090s. Right-hand side is the 370. So this is showing you track density in Southeast Asia, and then the changes from the historical period here. So if we focused on the most extreme example here, you see an increase in tropical cyclone tracks in the South China Sea heading into southern China and North Vietnam, winds from Vietnam. So she was particularly interested in that area. And you can see a decrease in tracks in northern China. Hatching showing significant differences. But we can also, with these simulations, look at the structure of the tropical cyclones and how those are changing over time as well. So not just look at the spatial changes in their impacts, their tracks, their rainfall and so on, but we can look at the actual structural characteristics of the tropical cyclones. So this is showing you a few different parameters. And I'll get you to mostly focus on the orange ones. That's the 370 scenario. And this is just the statistical representation. So the box and whiskers plot of all of the tropical cyclones here. And so in the first one, you're seeing the lifetime maximum intensity. And what we're basically seeing is that for the medium scenario, there's not much change over time, but for the more aggressive scenario, we do see an increase in that lifetime maximum intensity, including in the extreme value up here. For the landfalling, so this is landfalling maximum intensity, which is what Lynn was particularly interested in. You can see a slight decrease perhaps in the medium scenario, and then again an increase in the more aggressive scenario, in the landfalling maximum wind. This is the size parameter, so this is a radius of 25 knots. And interestingly here, we basically don't see any change in the size of the tropical cyclones over time or with scenario. But with the radius of maximum winds, we'd see a decrease in the more aggressive scenario. So the tropical cyclone size on average is not changing in these simulations, but the inner core size is decreasing, which is kind of interesting to me. And that's going along with an increase in the intensity, remember. So we've got an increase in intensity, which is where the maximum winds are going to be near that radius of maximum winds, obviously, and a decrease in the core of the tropical cyclone size. And we can look at that in a different way. This is looking at azimuthal averages now. So we're looking at the radius out from the center here, and then out to 150 kilometers on the left-hand side, out to 500 kilometers on the right-hand side. Top panel is vertical velocity at 500 hectopascals. So that's a measure of the updraft in the eye wall. Well, sorry, the updraft everywhere, but we're interested in the eye wall. And the bottom here, we've got the tangential wind. So what you're seeing in these pictures now are a decrease, and these vertical lines are helping to delineate this. So these are indicating where the maximum value at each decade is located on these plots, go along with the colors. And so we have a decrease in the radius where the maximum value is occurring in time through the end of the 21st century. And we're also seeing an increase in the maximum value. So an increase in the strength of the updraft, and it's also moving in towards the center of the cyclone. An increase in the maximum wind that's also moving in toward the center of the cyclone. In terms of the rain rate, we're not really seeing so much change in where the maximum rain is occurring, but it is also still occurring. Obviously, it's going to occur pretty much in conjunction with where the eye wall is located. But we are seeing this increase in the rain rate, mostly in the inner core area. And this is the fractional increase showing here, which is above the Clausius-Clapeyron expected value. And when you get out to the end of the 21st century, we're seeing up to a 35% increase in the maximum rain in the inner core. And that's an increase over our classes plateau. I'm not going to go through all of this. There's a really involved explanation of why we're seeing the decrease in the inner core size, the increase in the updraft, the increase in the intensity, when we have in environmental parameters. So the top is outlining environmental parameters. The bottom is just showing these inner core changes again. We have an increase in the environmental precipitable water just from adding those environmental perturbations that you would expect to see. But we also have an increase in the static stability and the convective stability that goes along with that. So we have this, on the one hand, moisture parameter that's increasing that you would expect to increase convection and maybe increase the intensity of the tropical cyclone, the rainfall that the tropical cyclone produces. But on the other hand, in the environment, we have this other factor that should be inhibiting convection and inhibiting intensification of tropical cyclones. Okay, so I'm not going to go through this whole explanation of why this works out in the end. But what I want to emphasize here is that using these simulations, we can look at what's going on in the environment and how that's impacting what we're seeing going on in the actual structure change of these tropical cyclones over time. We can also do hazard mapping. So this is work that Rubaya did in Bangladesh. So this is specifically aimed on Bangladesh because this is intensely what she was interested in for a PhD. And she ran the model, got physical parameters out of the model for tropical cyclones, looked at what the maximum rainfall out of her. She had 21 simulations to work with. There's not quite so many tropical cyclones have made landfall in Bangladesh as have made landfall in Southeast Asia. But she could pull out what the maximum rainfall was over her different decades and scenarios, what the maximum wind speed was across all those 21 cyclones. So she was producing a maximum hazard map. She also did storm surge modeling, but we didn't add climate perturbations to this. So this was storm surge, maximum storm surge produced by the historical simulations. And then she combined these together into a hazard map over here. Okay, so switching gears, this was the second topic on my title page, was looking at tropical cyclones feeding back on the Earth energy budget balance. And so the sort of motivation here was to understand that it's been estimated that the excess energy being accumulated by the climate system is about 300 terawatts per year annually. This is what's driving warming climate. So why would we want to look at tropical cyclones' impact on this, apart from the fact that I love tropical cyclones and that's what I do, because they're highly impactful and mobile weather systems that change the character of highly convective regions, particularly in the tropics. So that's one important point. Their annual global activity is highly variable, even though we understand that there should be about 80 of them globally a year. There's a huge standard deviation around that. And it also depends on how you count tropical cyclone activity. Is it in numbers of tropical cyclones? Is it in days? Is it in ACE? You get some very different ideas of the variability of tropical cyclones depending on what you look at. And then how their activity is going to change is obviously very uncertain. We really don't know in the future very much about how not just their activity and behavior, but their size and their structure are going to change. So this could be hugely important as well. And then a lot of the studies that are out there looking at tropical cyclones and climate change are predicated on the idea that tropical cyclones respond to a changing climate. But what if tropical cyclones themselves affect the climate? What if they impact back on the climate? Wouldn't their changing behavior then be potentially a feedback on the climate? Maybe in a good way, maybe in a cooling way. So this is really where we started. And in order to get at that, we had to start off by understanding how tropical cyclones actually contribute to the Earth energy balance. So the first one, and the one that I'm really going to show you a little bit of results on, is looking at how do they contribute to the Earth energy balance through their upwelling radiation. And this is a contribution that is due to their unique characteristics. So when I talk about that, I mean, if you don't have a tropical cyclone in the tropics, you still have tropical convection, but it looks quite different. It's not organized in the same way as if you have a tropical cyclone there that by its very dynamics and circulation is clearing out areas of the atmosphere and organizing convection in ways that wouldn't actually be there if it wasn't there. I don't have time to actually talk about the exchange with the ocean, but we've been doing some work on that as well. So just a couple of points here. So first of all, we've developed, first of all, a semi-supervised segmentation algorithm. When I say we, I really mean PN master student did this, that would go out and identify tropical cyclone cloud pixels and separate them from any other cloud pixels that were around. Semi-supervised segmentation, because we didn't want to have to do 20 years of this every half hour by hand. We've now got an actual AI that does it. And then once we've got those pixels, we can then calculate the radiation associated with those pixels. So we looked at 20 years of tropical cyclones. That's over 2,000 tropical cyclones. And the bottom answer was that what was the average tropical cyclone net radiation over 20 years, just due to their clouds, was equal to 55 terawatts of cooling, by the way, not warming, but cooling. So when you compare that to the original 300 terawatts of excess energy, maybe there's a significant contribution possible here. We can look at this by basin, and if you focus on the right pie chart, this is the tropical cyclone radiation by basin. You can see by far the greatest contribution is due to the Western Pacific. That's not surprising. You know, they have the most tropical cyclones out there, or they used to anyway. And then you can see the other relative contributions here, with the North Indian Ocean contributing very little. On the left-hand side, we can compare that to the tropical cyclone days. And we see a picture that starts to stand out a little bit, that we're not actually, we don't have an answer for this yet. But you can see that there's a couple of basins that contribute to that cooling radiation over their way, if you like. So they have less percentage of tropical cyclone days, but more percentage of tropical cyclone radiation contribution. And then you have some other basins that don't pull their weight in this sense. So their contribution to the radiation budget is less than their contribution to tropical cyclone days. So there's something going on in different basins that's a little bit different. So that's something that's interesting to look at. I'm going to have you just focus on this bottom left panel here. There's a lot in this diagram. So this is the important one. This is a spatial pattern of the tropical cyclone net radiation. Oops. So you can see that blue is cooling or net upwelling radiation, and brown is net downwelling radiation or warming. Okay, so mostly you see warming occurring over land when tropical cyclones are over land, but you do see some warming going on when tropical cyclones are over the ocean. But mostly it's net upwelling or net cooling going on, and it's going on in regions where we expect to see tropical cyclones. Okay, if you match this particular panel to the one up here, which is showing you the tropical cyclone density, they pretty much match up. You'd expect that. I'm not going to talk about the other two panels, just for time interest. This is basically the last panel where I'm throwing a whole bunch of figures at you. But these are some of the things that we can start to use to try and understand the differences in basins in terms of the net contribution to radiation. So the first one shows you globally that most of the tropical cyclones, this is just a frequency or a number histogram on the y-axis and the TC net radiation in terawatts over the lifetime of each individual tropical cyclone on the x-axis. And the blues are showing you net cooling or net upwelling tropical cyclones, and the reds are showing you where you've got net downwelling tropical cyclones. So there are individual tropical cyclones that contribute warming to the climate system, and tropical cyclones that over their lifetime contribute cooling. And why that is basically to do with the diurnal cycle of the radiation that they produce. So the net cooling ones actually produce more upwelling radiation during the daytime. Along the x-axis here, we have local standard time. And we have more upwelling radiation occurring during the daytime when you're getting reflection of the shortwave radiation. At nighttime, the long wave radiation contribution is essentially the same for both warming and cooling tropical cyclones. So it has to do with this diurnal cycle and whether a tropical cyclone is going to be reflecting more radiation during the daytime or not, as to whether they're going to be net warming or net cooling. And that has to do with, when you look on this panel here, seasonal cycles. So all of our global tropical cyclones have been rearranged so that they're all relative to the summer solstice on both these bottom panels. So a southern hemisphere cyclone looks just like a northern hemisphere cyclone here. And what we find is that globally, upwelling tropical cyclones tend to form earlier in the season, very close to or just after the summer solstice, whereas our net warming or downwelling tropical cyclones tend to form much later in the season, when the sun angle is much lower and you get much less reflection of that solar radiation during the daytime. This panel on the right bottom here is basically saying the same thing, where your net cooling, which is the blue here, tends to be when your solar elevation angle is very high or you're very close to the summer solstice. And as you move later in the season, you tend to develop more warming tropical cyclones when the solar angle is much lower. So these are some of the things we've been doing with this to try and understand how tropical cyclones impact the Earth energy balance. And what's of interest here is that we're seeing this very strong relationship with, for example, seasonality of the tropical cyclones. The other thing that I haven't shown here is we see a very strong relationship, not with intensity, but with cloud size of the tropical cyclones, which maybe is not surprising since the solar elevation angle and the amount of shortwave radiation that's reflected is very important here. But what's critical is that then the behavior and the seasonality of tropical cyclones into the future is going to very much impact what their net effect on the radiation budget is. And we don't really know what that is. The very last slide of mine is a plug. So in Australia, we've just started up this new Centre of Excellence for Weather of the 21st Century. It's an Australian Research Council funded centre for 7 years. It's a collaboration across 5 universities and is actually distributed across those 5 universities, which is a very interesting structure to have for a centre, research centre. Collaboration with a number of government organisations in Australia, federal and state, a number of private industries, and a number of global partners for whom they're listed here, but I didn't have their cool logos to show you, but they're all listed here, and some of them are in this room, although the particular PIs might not be. The fundamental aim of this Centre of Excellence is to try and understand climate, how the weather that impacts us on the ground is going to affect us. So how does the weather change affect us going out to the end of the 21st century? So instead of looking at climate statistical factors like how are temperature extremes going to change, we want to look at actually how the weather is going to change and how that weather then affects us on the ground. When we talk about, and these are the different projects that are sitting underneath this centre, when we talk about high impact, for example, we're not just talking about extreme floods and extreme winds. We're talking about wind droughts. We're talking about things that affect energy production under green energy. We're talking about things that affect wind farms and transport services and that sort of thing. So the main reason I wanted to bring this up was because it's a new thing in Australia. It looks like it's very Australian-centric, and well, it is. But we're looking for collaborations across the world because we believe that the research that we do in this centre is of interest to globally, and we're also very much aware that research that occurs globally helps us to understand what's going on in Australia, and I think that the partnerships are extremely important. So with that, I'll say thank you for listening.
Thank you very much. Maybe. Yes.
I don't think you explain how you estimate the radiation that is caused by, affected by the tropical cyclone. You say that you get the matching cloud pixels with series. So at each 6, sorry, okay.
So at each, we've got half-hourly satellite imagery that we work out which pixels are tropical cyclone related, and we match that to the CERES data sets for long wave and short wave radiation. That means there is a horizontal resolution that needs to be accounted for. And so in going to the coarser CERES data set, that is coarser, we do a what do you call it, a partial. So the SARS data set is something like 4 times lower resolution. And so we'll do a part, if there's one pixel that falls within a cirrus pixel, that is a tropical cyclone cloud, then it'll get a quarter of that radiation that's at that cirrus pixel. And then also interpolate in time. When I said that, what we did was just a statistical relationship with the intensity of the tropical cyclone on a particular day and the value of the radiation calculated that daily and the daily summation of the radiation due to the tropical cyclone. And then you just plot that on a plot across all tropical cyclones, and we see no. So a more intense tropical cyclone doesn't necessarily produce more upwelling radiation, for example, than a weaker tropical cyclone. That's mostly because it's more due to the cloud fraction than it is due to a wind relationship. But the spatial extent of the clouds matters. So a larger tropical has more influence. And I can show that. I've got pictures on here. I can show you that.
Hi, Liz, with the mic. Thanks for a very interesting talk. So the radiation caused by tropical cyclone. Oh, okay. So the radiation for the tropical cyclones, you calculated them on during the lifetime of the storms. Have you looked at the impact, for example, 1 week or 2 weeks following the storms, and see how the net impact of TCs on the clouds? Because in our paper back in 2017, I think we look at the SST following the TCs during the week after the TC passage, and seeing that the TCs actually reduce the low cloud amount and inducing an increase of shortwave radiation.
Yeah, no, that's a really good point. No, we haven't looked at that. Yeah, but we've thought a lot about how tropical cyclones affect the general tropical clouds. We have to imagine if a tropical cyclone wasn't there, what would you have instead? And so we've tried to imagine that because we don't know. And that's a very good point, that in the 1 to 2 weeks following the tropical cyclone, you may well see a clearing of the clouds because of, downwelling Rossy wave. So that's an interesting question. And we'll have to think about that more with you.
Okay, thank you.
Thanks, Liz. I really enjoyed talk. Actually, I have 2 questions if I'm allowed to do that. The first one is, so in the first part of your talk, you in the beginning, you introduced the reduction of TC frequency in the south part of A9, is right? You can remember, you can really trust my really bad memory. Then when you finish your first part of talk, you say, okay, in your WRF simulations on the worst scenario, you actually see the increase of TC frequency in the southern part of South China Sea. I don't know how would you interpret the difference between the observations and the models. The second part is that, have you considered the remote impact of TC on from the net radiation perspective? For example, we have forecaster colleagues in Malaysia. They are using the TCs east of Philippines as the indicator showing, okay, we are going to have a very dry condition in Malaysia because the typhoon actually is happening in Pacific. So I'm not sure how would you consider this remote impact of TC on the global energy balance?
So second part of the question was basically the same question I think that was just asked. And we haven't addressed that, mostly because we're only looking at the radiation contribution due to the pixels of the tropical cyclone itself, but we are doing that relative to the background state, which we calculate for each day as well. So we're looking at background state, and we're calculating the contribution of the tropical cyclones relative to the background radiation state of the clouds that are outside of the tropical cyclone. So make sure I've got that. I'm just thinking through my head to see if I've got that correctly. Yeah, but our background state isn't zero radiation, and we're just looking at the tropical cyclone. Our background state is taking in the radiation contribution from all of the clouds that are out there. So we are taking into account if there's a clearing when we look at the relative contribution. But I'm not sure if that actually answers your question, but we are taking it into account in our calculation. Your first question, we're only looking, so for, I think what I showed was future climate simulations. We don't have any observations that we can actually compare that to. Right? So I can't answer that question. I think that, but if that was the wrong, perhaps you could come and talk to me later if I didn't get your question correctly.
All right, thank you again, Liz. Now we will move on to Falko Judt from NCAR, talking about tropical cyclones in global cloud resolving models.
All right, good afternoon, everyone. So this is going to be pretty much a model evaluation study, so it shouldn't be too intellectually demanding. But looking in the room here, I think most of you don't really know me, so I thought,
maybe you need to click back on.
it was working there. The arrow keys, right? So yeah, as I said, most of you probably don't really know me, so I'm a blank slate to you. So if you try to fill that in first, even though I'm from NCAR in the US, I actually grew up on this side of the Atlantic and in northwestern Germany. And since I was a child, I was fascinated with hurricanes. Problem is in Germany, they don't have hurricanes. So I started studying meteorology in Leipzig, and then kind of mid-late undergrad, I moved to Miami, Florida, because I thought I want to study tropical cyclones where they actually happen. Turns out I never experienced one in my years there, and that's where I got my degrees. And then, you know, as life goes, I got a postdoc at NCAR, the beautiful Mesa Lab there in the back. And so I traded the beach with the mountains, and now I'm landlocked again without any tropical cyclones, but I'm still doing tropical meteorology, atmospheric predictability, and you may have seen a baby around. This is her little brother. We left him at home in Colorado. Actually, I'm just kidding. He's with my parents right now. So that was about me. Let's talk about the work I'm presenting here. So I'm going to start with the premise. And the premise, I think most of you agree that current weather and climate models are not really doing too hot in the tropics in the sense of good forecasts. When you're a forecast user, let's say in Africa or somewhere else, the models are really not that good. No matter if it's GFS or ESMWF, you name them. So I think we probably also agree to some degree that this hypothesis is probably true, that the current generation of models is lacking resolution in the sense that, that we need to use cumulus parameterization to account for cumulus convection, and that introduces a lot of problems. I would say introduces a lot more problems than it solves. So this talk really is about a demonstration what we could have with advancing computer power, bigger computers. We can crank up the resolution, and we can run global cloud resolving models. So global models with kilometer scale resolution. And this is just some eye candy to show you how beautiful our depiction of the atmosphere really looks in these high resolution simulations. So there's simulated clouds. On the left, you see a tropical cyclone making landfall in Vietnam, and that's a depiction of 2-meter temperature right there. To show you really the effect of cloud resolving modeling at global scales, I'm gonna show this example using the MPAS model. So MPAS stands for Model for Prediction Across Scales. It was developed at NCAR in the mesoscale and microscale meteorology lab where I am. You're probably familiar with the WRF model. So MPAS is very similar to WRF. It's just a little bit more updated in the sense that it can do global and regional applications. It's an unstructured mesh. It's essentially, we don't want to call it a successor to the WRF model, but it can do a lot of the things that the WRF model can. And we're promoting now MPAS. So again, MPAS is similar to the WRF model, NWP research, but can also be used for forecast applications. So what I mean by resolution ensemble is that I ran 8 or so simulations, and the only difference is the horizontal grid spacing. So we're starting with, this is our nominal diamond run. So this is global, 3.75 kilometer. And then we just essentially decreased the resolution all the way down to really coarse 480 kilometer. I don't know, that's probably a climate model from 50 years ago. In the interest of time and to make it not too boring, we're going to be focusing essentially on 3 simulations here. 3.75 kilometers. This is, again, kind of future weather and climate modeling. A 15-kilometer run. This is supposed to be like a current NWP setup, operational NWP, so GFS, ECMWF, and so on. And then I have this simulation that's supposed to mimic kind of a CMIT type old school climate model. And all the results I show are from these 3 runs, and they were all 40 days long, covering a period of in the summer of 2016. And they were all initialized with ECMWF data and then run out for 40 days, and the SSTs were updated, also coming from the ECMWF model. All right. So first, let's start out very simple. On the top there, you see 3 satellite images of Hurricane, I think it was Irma, or no, actually it's Hurricane Maria of 2017. This is the same image. We're looking now, this is how a hurricane would look like in a 120-kilometer MPAS. Bunch of big pixel. Not really realistic. Now you're going down to 15 kilometers and you're starting to get the features that make up a tropical cyclone. You get a cloud-free eye, you get some banding features that resemble rain bands, but it's still pretty pixely. And then you jump into the 21st century, and this is what you get with the 3.75 kilometer resolution. So I like to show this to people who don't study tropical cyclones and don't know much about climate models. And I say, well, you really trust climate models that produce tropical cyclones that look like that? It's a question, I think, that we've been discussing for a while. Now for some more quantitative analysis. What I'm showing there is the tracks, observed tracks using IB tracks from that August-September 2016 period. The numbers indicate numbers of tropical cyclones in each basin. You notice here, they're all tallied up here on the right. So during that 40-day period, there were 24. I think I'm only counting tropical storm strength and stronger. So when you run the MPAS that mimics a climate model, you're severely underestimating the count. That's probably nothing new to you guys. It's just nice to see. So this is clearly not working. Interestingly, it doesn't do anything in the Eastern Pacific, but it captures quite a bit in the Western Pacific. That's probably deserves a study of its own. Now, when we're going to what a global weather prediction model looks like today, you're increasing the number of TCs that you get. You're doing better. You're definitely moving in the right direction. But then when you're using the global cloud resolving model, suddenly you're very close to the observations. And this is actually not tuned. It's just happened to be. So we're pretty happy to see this. Again, it's one case study, so I don't want to say, I wouldn't put too much faith in it, but definitely we're getting going in the right direction by just increasing the resolution. All right, so this is tracks and number of tropical cyclones. How about intensity? Because we all know that climate models are really bad at getting the intensity right. And again, that's no wonder because the intensity of a tropical cyclone is really determined by the eye wall, a mesoscale feature. And with the 120-kilometer model, you cannot resolve the eye wall. So you're getting something like this that never reaches hurricane strength if you're not tuning the model. Straight out of the box MPAS here at 120-kilometer resolution. The light gray lines here in the background, that's the observations duplicated from the top, so you get some easier way to compare the two. Now, once you move to 15-kilometer resolution, you're definitely getting better. But of course, even with 15-kilometer mod resolution, and this is the grid spacing, so not talking about effective resolution here, but you're still missing the really intense ones here. Those were some Western Pacific typhoons that reached major hurricane strength. For easier, like you can see the categories here that makes it easier to see how strong the storms were. And then when you go to the cloud resolving model, again, everything is the same except the horizontal resolution. Now you're actually creating something, or the simulation looks like observations, at least statistically, right? Again, this is a 40-day free-running simulation. We're not expecting it to capture the individual cyclones that actually happen. This is, I think, a pretty good visualization of why a lot of folks, at least on the weather side, say, well, increasing the resolution really is useful. It's not it doesn't get rid of all the errors and biases, but at least for intensity and strength and so on, it's one way to fix the biases. To sum everything up, this is the accumulated cyclone energy from this 40-day simulation. Top is the observations with an error bar. You can read the paper, how the error bar was calculated. And you notice here, well, of course, the low resolution versions are quite a bit too low because they're not producing the number of TCs and they're not producing the right intensity. Now, the 4-kilometer or 3.75-kilometer run is overshooting a bit. I'm not too worried about that. First of all, it's not coupled to an ocean. And secondly, I think there is some evidence that 4 kilometers is really marginal, and you tend to get too strong of updrafts sometimes. And I think they spin up a few TCs that are too strong. Not really sure about that, but that could be one of the reasons for why the 3.75 kilometer simulation is overshooting a little bit, but at least it's in the right ballpark. Okay, so I know this meeting is about tropical cyclones, but I want to branch out a little bit and talk about tropical waves. Because when we look at the tropical cyclones, we notice like, well, they're clearly better in the 4-kilometer run. How about the tropical waves? And skip this nice video, which is Rosimar's parents' backyard in the Puerto Rico when a tropical wave moves through. I assume everyone here knows a Hofmüller diagram. Who does not know what a Hofmüller diagram is? Nobody. Good. We can skip this. There's a Hofmüller diagram of precipitation from August 1st through September 10th, 2016. What you see here is obviously nice, these slanted lines, which are just waves propagating east and west. There is a very dry area, which is just the Eastern Indian Ocean here. Then you see here on the left, this is where the African easterly waves, actually no, these are the African easterly waves here around 0 degrees longitude during this time period, and this is just the Western Pacific warm. So when we plot the same Hofmüller, but we're using a climate type model, you're getting this. So you're not really seeing much in terms of propagating waves. All the heavy precipitation is anchored over the Western Pacific, where the SSTs are warm. That's what the cumulus parameterization does. It knows it's warm, warm SSTs, it's moist, so we're producing rain here. 15-kilometer doesn't improve much, but when you go to 3.75 kilometer, you see the step change towards more realism. And so we're, again, really happy with this result, showing like, well, you're getting a lot benefit by just increasing the resolution, not doing anything else. This is just another way to look at it. It's rainfall anomaly as a function of wave phase. So clearly there's a wave propagating through from the observations, from the low res simulation, from the medium res simulation, and from the high res simulation. Getting much better agreement with the observations. Okay, this is the last thing. Again, you probably guessed it. This is a frequency of rainfall intensity, and 120 kilometers doesn't produce much heavy rain. 15 kilometers gets a little bit better, but you get the biggest improvement when you go to explicit convection, turn off with deep cumulus parameterization, and then you're getting something that looks very close to the observations. All right, that was all the good stuff. Now we're going to the not so good stuff. This is the iconic image from the diamond paper, where we see one real world and 8 fake worlds. I'm not going to ask you which one is the real one. I just want to point out that all of them look realistic, but all of them look different. It's not like we're converging to the truth when we're using high resolution models. They're still very different from each other, even though they're all very realistic. And this is a depiction of the strongest hurricane in each of the diamond models. They all run that same period. And I just picked the strongest storm at peak intensity. Now you see, like, when you know hurricanes, you can tell that this one is way too strong. So there's the color bars down here. The Arpège model from France is just producing storms that are way too strong. They know of the problem. They have since fixed it. The Icon model from MPI or Deutscher Wetterdienst in Germany produces storms that are way too weak. The SAM model, I don't know what's going on with SAM. It's really weird for this simulation here. And if you think about, well, what looks realistic, I would say FE3 looks realistic, MPAS looks realistic, GEOS probably also looks realistic. Was a little bit coarser, but also looks realistic. The IFS again was a little weird. Okay, so I've showed you this before. This is MPAS and MPAS ACE versus observations. When you look at the other models that are all have similar resolution, cloud resolving, there's a huge variability. So one of the big problems with these models is they're not converging to the truth. The variability is just as large as for standard old school climate models. One of the big hopes was that they're kind of converging to the truth. I don't think that's happening, unfortunately. Is there one model that's better than the others? No, I don't think so. On the top there, you see GEOS from NASA in black. Oh, that's the pressure wind relationship, by the way. So maximum wind speed on the x-axis, sea level pressure on the y-axis, black observations, orange is the model. And that's a great agreement that the GEOS model is showing here. MPAS is pretty good, a little bit too weak for a low pressure. And then the IFS is a little bit off there. Now you look at the size. What's plotted here is I think the average 34 knot wind radius per quadrant in black observations and orange the model. So again, almost perfect agreement for GEOS. I mean, if you see these two images, you would say, why are we not running GEOS for tropical cyclones? MPAS is a little bit too big. IFS is a little bit too small in general. But now the problem with GEOS is it produces way too many storms. So frequency is way off in that model. Now MPAS is better and IFS is also better. So this is just to illustrate that there's no model that is the best. It depends on what you're looking at. The last thing I want to mention is, and that's the biggest hurdle when it comes to global cloud resolving modeling, it's that's just computationally very expensive. When you run a 120 kilometer MCAS for one day, you use this amount in core hours, 2.53. It's almost negligible. You run a one-day simulation with 15 kilometers. It costs about 2,000. Let's call it 2,000 units. So how expensive is the 3.75 kilometer run? this much. So of course, now if people go to the climate community and say, well, why don't you run 4 kilometers instead of 120? Well, if you have a computer that's 93, or it's actually a factor of 32,000. So if your computer is 32,000 times faster, then you can run the same simulations that you can run nowadays with 110 kilometers. So I don't think running global cloud resolving models is going to solve all the problems that the community is facing. I don't think it's, there's a disagreement. I'm just going to mention the name, Bjorn Stevens, right? Should we just ditch all the 120 kilometer models and just run global cloud resolving? I don't think, knowing this figure, I don't think that's the solution. With that, let's close here. Just 4 bullet points, 2 good ones, 2 not so good ones. So global cloud resolving models really reduce some of the long-standing biases. Hurricane intensity, size. I haven't looked at rainfall. That's still outstanding. And they better capture tropical rainfall variability in general, especially with tropical waves. But there's still this large intermodal spread, so there's no convergence towards the truth. That's definitely a big problem because they're also very expensive. So that's so I always like to say, I think this is one nice tool we have to address a lot of the problems, the global cloud resolving model, but there's also downsides and probably worthy of some discussion how to include this tool in our arsenal. Thank you.
Thank you very much. I'm going to go in order of 10.
Thank you. I have a comment and a question. The comment is that back in 2008, Shukla proposed a international consortium to develop computers to do kilometer scale modeling. It didn't happen. That idea is being resurrected by, of all people, Kelvin Drogemeyer. And that group very much needs to see your talk. With your permission, I'd like to send a link to it, especially the second half about model differences.
Yeah.
My question is about a lecture we heard last week from Florian Pantillon from Toulouse, who showed Medicaid Llanos simulated at 1 kilometer and then 200 meters. And at 200 meters, structures arose that weren't seen at the kilometer resolution that were a couple of kilometers across. Pierluigi and I looked at that and we both came to the same conclusion that it looked like it was the 1 kilometer was overly diffusive, and we were thinking that it's the turbulence closure, which was Smagorinsky diffusion. Has MPAS thought about the validity of turbulence closure schemes that were developed for 400 kilometer models being extended down to this regime? And are we at the risk of, like some of the results you show, of being overly diffusive?
So MPAS is coming from the mesoscale modeling world. So the turbulence parameterization is inside the EBL scheme, and I think in this case is MYNN. So it's not really I'm not too familiar with the climate models, but I think it's a very different parameterization that comes out of the weather model world. So what that means is I'm using that also for a 480 kilometer grid or 480 kilometer grid spacing run. So that's questionable. But I think this is all the physics are tuned for a couple of kilometer scale grid. We're trying to develop scale aware physical parameterizations that work across orders of magnitudes of resolution, but I don't think we're there yet. So for this just the simulation that I showed, it's all the physics are tuned to work well at 3-4 kilometers.
There's a whole community of turbulence closure theorists that we don't seem to be exploiting. That's why I raise this issue.
Yeah, it's a good point.
All right, I'll ask my question, and I'll send it down to Cheyenne because I think I saw your hand too. So similar to Michael's question, I'm going to play devil's advocate because I'm also going to talk about 3 kilometer models tomorrow, but you kind of just hit on a point that I think makes those first 2 bullet points. I'm not, so you're taking a model that's been developed to run really, really well at kilometer scales, like a weather model, and then you're kind of coarsening everything to look like a climate model. Whereas this is actually a common critique from the weather modeling community about climate modelers when we turn up the wick on resolution is like, you're not retuning anything. Like you could do way better than this. So my question is on the tropical rainfall variability. So ECMWF has actually done some work that shows that some of the biases in the drizzle mode are actually all just deep convective errors. And that even at 15 kilometers, if you turn off deep convection, you actually get a pretty realistic looking like Wheeler colitis diagram. And so my question is, have you explored any of these potential avenues? You know, it's a tricky question because I know you're trying to do this just to isolate resolution, but I suspect some of what you're seeing, especially at 15 kilometers, is due to this parameterization issue. I was curious what your thoughts were on that.
I agree. So the same, criticism that we leverage at the climate community is certainly valid here because it's all tuned for weather for kilometer scale models. I still think the underlying result stands that going from 10, 15 kilometers to 3 kilometers gives you a step change towards more realism. But I cannot totally refute your criticism. It's certainly valid. So I haven't, well, we actually did run 15 kilometers without the deep convective scheme or with the old Tietke scheme, and it just looks as ugly as the 15 kilometer run that I showed. So I still believe the results are robust, even though I cannot now say we tried everything else.
Actually, my question is kind of similar to Colin and Michael's questions. So,
and we had Josh, then back to you.
I have two questions. First, a very interesting talk. As you showed in the previous slide, the 4 kilometer resolution is not feasible for climate prediction or projection. See, if we go with like a 15 kilometer resolution, like the model does not do like as good a job as in terms of tropical precipitation. But if we look at other variables, for example, like meridional wind, to evaluate tropical wave disturbances, do we have a kind of like a reasonable representation for tropical wave disturbances?
So I haven't looked at that, and that's certainly something that could be that 15 kilometers is good enough for those kind.
Okay. My second question is kind of linked back to Liz's earlier talk. We know like coast resolution climate models do not well represent tropical cyclone intensity and tropical cyclone frequency. So if there is a strong feedback from tropical cyclones to the climate, and the coast resolution model does not get the tropical cyclone statistics right, is there something missing? And does that something affect the climate state of the coast resolution model? So have you compared the climate state or the mean state biases across different resolutions?
Yes, we have Rob Nystrom at NCAR. Well, he's moving on, but he has done some. I think he has run 15 years of 40-day long simulations and compared also the low res to the high res, and the biases are still there. So there's model specific biases that MPAS probably has. For example, there's a lot of shear over the, it's not the main development region, but somewhere over the tropical Atlantic, when you compare it to reanalysis, the MPAS just produces too much shear no matter what resolution. So there's certainly some aspects that get better by increasing the resolution, but there's also other aspects that don't. And since there's essentially a million things you can you can validate, it's just very hard to come up with one answer to the question of how much improvement do you get when you increase resolution. You know, I showed the positive results with the intensity, but we know that it's not just nice to see it happening. Yeah, so other things I'm not sure if you actually get them.
Thanks for an excellent talk. You may have covered this already, but I just wanted to ask if you had a sense for the one of your conclusions there is that you've got large intermodal spread. Do you have a sense of how large that intermodal spread is compared to the coarser resolution models? I suppose you're going to be limited by the number of runs you can do.
Yeah.
But,
yeah. This is just anecdotal, but I think the spread is as large, if not larger. So there's only 9 or 10 centers that can do the cloud resolving models versus like, I don't know how many models are in CMIP. Yeah, so it's different to compare when you have only a couple of models, but just me looking at them, I was disappointed to see that amount of spread. But I don't know if anyone has looked at the spread in the cloud resolving model versus classic CMIP or high res net models. Would be interesting to see.
Very nice talk, Falko. So I have sort of 2 interrelated questions. One is like that you showed these basin differences in your high resolution runs, or sorry, in your lower resolution runs, the basin wide differences in frequency, how it compared to reality, where the East Pacific had fewer, had 0 at coarse resolution and compared to the West Pacific. And I'm wondering whether you think that possibly the systematic size differences that we see where East Pacific storms tend to be smallest globally and West Pacific are larger, if that could be a plausible reason for that difference. And then more broadly, I'm wondering if you thought about how the importance of being able to simulate genesis processes versus the importance of simulating the precursor disturbances and biases and that you get from coarse resolution, how the relative importance of those in terms of frequency.
Let me try to answer the first part. I think the size difference is one thing. I also think the other thing is that the precursor disturbances are different in the Eastern Pacific than the West Pac, because you get the Eastern Pacific is mainly waves, and the low-res simulations didn't really produce many tropical waves, whereas the Western Pacific, a lot of it is monsoon trough and some intrinsically larger scale phenomenon. And I think that's why you get it. For some reason, the model can simulate those processes more realistically, even at low resolution than whatever happens in the East Pac. Yes, and certainly the size difference plays a role too. The second question, I don't have a good answer to that. Yeah, I don't know. I don't want to speculate too much. I always want to say that with explicit convection, you're just way more realistic, way closer to the real world than when having a cumulus parameterization accounting for all the stuff that's going on. So I think that the genesis process is more realistically depicted in a cloud resolving model than in a non-cloud resolving model. That's my intrinsic feeling, but I don't know how the precursor disturbances are affected.
Thank you.
Thank you. We'll close here and reconvene, I suggest, in 20 minutes here. So it's now 4:23. So let's reconvene at 20 to 5. Yeah, see you.